we're trying to do with these sessions is we're trying to put some focus in trying to find ways for all of our customers to lower their operating costs without jeopardizing production, and also at the same time get some education as to proper operations of plunger lift to help reduce breakage and continue to find ways to constantly increase production as well as reducing our operating costs. And so we're going to get started today with our gas assisted plunger lift. So we will cover today what is gas assisted plunger lift. We'll take a look at the benefits of the system. We'll look at candidate selection. We'll talk about all the things that we need to look at to ensure that we've picked the proper candidates that have the best chance of success and increasing of production while lowering your operating costs. We'll look at gas lift operations or optimization, because that's where it all starts with. We've got to be able to optimize our gas lift system to make sure that everything is nice and efficient before we try implementing our GAPL system. We've got some example wells to go through how it is that we put together all the necessary information and what it is that we're looking at in order to make sure that we've got the least amount of changes that have to be done to the well. We'll take a look at the installation of the plunger system. We'll go step by step on how to get it installed. Then we're going to look at optimization. We're going to look at what we've got to do to be able to get the system optimized and what the differences are between a regular bypass plunger and our GAPL system. We do have some case studies to share with you guys. Majority of these were down in the Eagle Ford. And then we'll finish things up with the question and answer period. So what exactly is a GAPL or gas assisted plunger system? It is simply a hybrid method of artificial lift where we add a continuous flow plunger system into an existing gas lift well to increase the overall efficiency of the system while increasing production. The type of plunger that we're going to use is most normally a bypass or continuous flow plunger, but it is possible to run the system with a conventional type or a fast falling style of plunger, depending upon the application. If we're going to run a bypass plunger, it will be with continuous gas lift injection. If we're going to look at a conventional system or a fast falling type of plunger, it will be an intermittent gas lift system, as we will have to shut the well in to build up pressure to help overcome lower gas rates. The addition of this plunger system can help eliminate a lot of the most common gas lift inefficiencies. The first one is it helps with optimization of our injection. Most importantly, it helps us eliminate over-injection of our system. And this is due to the fact that the bypass plunger does not require as much gas to cycle. The rule of thumb is a bypass plunger only requires approximately 70% of the critical rate of the well to cycle, whereas the gas lift system requires as close to that critical rate point as possible for it to be able to stay optimized. The normal flow of a gas lift system is always going to be slug flow due to the injection of gas. And the plunger is able to help improve this and greatly reduce any liquid slippage that might be happening due to the slugging effects. But the big one is paraffin control. All gas lift wells will see some level of paraffin buildup due to the cooling effect of the injection gas. Since the plunger improves the overall flow of the well, it greatly reduces the chance of the formation of the paraffin. And this is the initial reason why people started to run plungers in gas lift wells to begin with, to help reduce with that paraffin in the upper section of the tubing. And so we would run the plunger just to be able to reduce that formation. The improved flow of the well due to the plunger happens for a couple of reasons. The first one is that the plunger is able to provide that nice tight mechanical seal to the tubing wall, which greatly reduces that chance of slippage. And the second reason is that because we're able to get so many cycles from a bypass plunger, we're able to help change the flow of the well from a slug flow to more of a transitional type flow regime, or as closely matched to a natural flow as we possibly can. Since we're able to improve the drawdown, because we're able to reduce the slug effect, we're going to start seeing our casing pressure drop, which in turn is going to reduce that drawdown and give us more production. And then by keeping all of our fluid and gas moving more efficiently, we're also able to see a much more stabilized flow from the well, which in turn helps increase the overall efficiency of the gas lift system. But this will still not take this gas lift system all the way to depletion. We're still going to have a little higher flowing bottom hole pressure due to our injection gas having that pressure behind it. But because we've got that plunger in place and making the system a lot more efficient and reducing the amount of injection or buyback that we may need, it allows us to delay that CapEx expense of that rod pump and put it onto the well much later in its life when it becomes much more economical to do so. With a smaller unit, we've got to take a look at how much formation gas is the well actually producing versus our injection. I like to take a look at rod pump operations after the well gets down below 100 MCF of gas. As long as we're producing more than 100, the system is going to be more beneficial to have a GAPL on it versus going to a rod pump, where we may have to deal with pump problems and rod problems. So now we can take a look at candidate selection. It all starts by looking at fluid rate versus total gas. Ideally, we're going to be looking for wells that are producing about 250 to 300 barrels per day max to start with. However, it is possible to lift up to about 400 barrels in 2 3/8 tubing and about 800 barrels in 2 7/8 tubing. Although these higher fluid rate wells are really more due to paraffin issues, and we're going to run that plunger to help relieve that issue in the upper section of the tubing string. So we've seen a lot of improvement in that respect with these high fluid rate wells. And in some cases, we have seen some production performance enhancements, but that's not why we're running them in those really high fluid rate wells. When we take a look at liquid to gas ratios, we're looking at equivalents to about 350 to 500 barrels per million of gas. And that is going to be our injection plus our formation. And this ratio is very dependent upon the fluid cut. Obviously, the higher the oil cut, the lighter the weight of that fluid column is going to be, and the more fluid we can expect to move with our GAPL system. We have seen a lot of success with the lower GLRs. It does come down to economics. The wells that have got the lower gas rates, if you've got a higher oil cut, the gas lift system with the plunger system is going to be much more cost effective than going to a rod pump operation. Your LOE for your plunger system is just the replacement of a plunger. So, you know, $200, $250. We do need to take a look at line pressures. If we've got wells that have got badly fluctuating line pressures, we may not be able to lower our injection rates because we have to make sure that we've got enough injection rate to handle those increases in that line during the normal operations throughout the day. When we're looking at this application, it is important for us to keep the GAPL system in mind from the beginning when we first put in our gas lift well. If we know that these wells are going to deplete below 400 barrels a day, we can plan ahead by installing an X nipple above the bottom valve, or ideally the orifice. And the benefit of the orifice is it allows us to be able to lower the injection rate as much as the well wants, and we don't have to worry about closing of a valve. So we can just put in the system whatever the system needs in order to be able to keep that bypass plunger in good operation. And a packerless completion can also be very beneficial. It allows us to be able to get the injection as deep as we want, and we're not limited to where the packer is going to be set. So we can U-tube our injection gas around the end of the tubing. We are normally setting our packers around 40 degrees, and this allows us to be able to put our end of tubing much closer to our heel. And the sooner we can introduce better gas velocities into the system, the more efficient the overall system is going to become. We are still limited with plunger lift. With bypass plungers, we don't like to run them deeper than about 50 degrees, and that's really due to wireline operations. Our bottom hole spring starts to lay too far against our tubing wall, and it becomes very difficult to retrieve for inspection. And then with a conventional plunger, if we're going to do intermittent, we're going to be limited to about 30 degrees. And the reason being is because the plunger is actually stopped for a period of time. If we go too deep into the curve, we'll have too much surface area of the plunger on the tubing wall, and it will cause a lot of drag, and the plunger may never come back up to surface. And then wells with strong formation gas become really good candidates also. having the ability to continue to reduce the injection rate as low as possible. And in some cases, and we'll show you with a couple of our case studies, we're actually able to turn off the injection and look at releasing the compressor, and once again, lower our LOE costs. Successful GAPL implementation starts with the optimization of our gas lift system though. If the gas lift system is not optimized first, the chances of us running our plunger are going to be very low. And it all starts with our gas rate, total gas rate, injection plus formation. And then we're going to compare that to our critical rate. And we like to look at downhole critical rate versus surface critical rate because we have to make sure that we're taking into account our fluid. And that's the problem with surface critical rate, with the Turner critical rate, is that it doesn't take into account enough fluids. Then we're going to take a look at our casing pressures. Are our casing pressures fluctuating? This could be an indication of over-injection or under-injection. If the well is not getting enough gas, we could be seeing a much higher level of slugging, which could cause the casing pressure to increase, causing the valve above to open up. And then once the well unloads, we see that casing pressure drop, moves back down to the lower valve, and it goes back and forth until we actually increase our injection. Same issue with over-injection. If we're trying to put too much gas into the system, we can either start holding back fluid, or we could actually overrun our port size and the ability to pass gas through a single port, and that will cause our casing pressure to increase and open the upper valve. And this is what we would refer to as multi-pointing. It's really important for us to understand the minimum injection rate that each port can pass. We always take a look at our port size and looking at how much gas can I put through that valve as a maximum value. For GAPL, it's really important for us to understand what the minimum is. For a 12-port valve, we have to be injecting at least 100 to 200 MCF of gas for it to stay fully open, depending upon our tubing pressure or our casing tubing differential at the injection point. The lower the differential, the less gas that can actually pass across that valve. With a 16-port valve, we need to be injecting a minimum of 350 to 400 MCF. So it's really important for us to be taking a look at how much gas am I really going to need to inject to optimize my well when I'm deciding what size port I'm going to use with my gas lift system. And this is why an orifice on the bottom is so advantageous. There is no minimum gas rate requirement, so we can inject whatever the well needs and not what the valve needs. That's a really important thing to consider when we're taking a look at this system, live valve versus an orifice. A lot of people prefer to go with the live valve just because it gives you all the troubleshooting ability of our gas lift system. But in some cases, if we're only going to be injecting real low amount of gas for this type of system, it might be best to go to an orifice at that, doing it at that time. The last thing is tubing pressure. Is our tubing pressures fluctuating? Is it possible to get our tubing pressure lower? We all know the lower the tubing pressure, the lower my critical rate requirement is going to be, so the less gas that I'm going to probably have to inject into my system to make this system work properly. The next thing we have to do is we have to take a look at where we're actually injecting. And the way we determine this, or the easiest way to do this, is we take a look at our design report. And every single vendor is going to provide you with this design report. What we want to do is identify our casing pressure. And we're going to come over here and look at this column right here. PSC stands for pressure surface closed. As long as this value is greater than our casing pressure, it means that this valve is now closed. So if I take a casing pressure, for instance, of 950 PSI, I can work my way down this column. As long as the value is greater than my casing pressure, it's closed. So I can come all the way down to valve 4, 961, so my valve is closed. Next valve is 941, my casing pressure is 950, greater than this value, therefore these valves here are open. So this becomes my injection point. So in this case, I'm injecting on valve 3. Now if I've got 850 PSI, that is less than all of the pressures in my PSC column, and therefore I'm injecting on my orifice. So I'm optimal for my GAPL system. And then here is our critical rate chart. Critical rate is just simply the minimum amount of total gas that my well requires for it to be able to stay flowing. In this case, we've got these curves on here that have got different fluid rates, because fluid rate is really critical when we're taking a look at our gas lift wells. If I have a well, for instance, that is making 100 barrels a day, this line right here, I've got 100 PSI flowing tubing pressure. So that means my critical rate downhole is approximately 530. So what I do for my GAPL system is I now can identify my target total gas rate, my minimum amount of gas that my bypass plunger is going to need to see for it to cycle. So I will take 70% of that value, and that becomes my target. So in this case, my target or minimum gas rate requirement is approximately 375 MCF. So in other words, my total gas rate, formation plus injection, needs to be as close to 375 as possible. The one thing we have to keep in mind when we do take a look at critical rate is that these charts are just a starting point. Depending upon the condition of our reservoir, the way that our horizontal lateral is completed, we may see a lot more slugging, and therefore this value may be a little higher or it may be a little lower. But we need to be able to have a starting point, and that is the purpose of this. This is our starting point for optimization and our starting point as to where it is that we can possibly reduce our total gas rate down to make my plunger run. So that's where we're going to get started. So now what we can do is we can start taking a look at an example to figure out how it is I'm going to identify what a good candidate is and how I can optimize the system. So what I'm going to do is I'm going to collect my average formation gas rates, what my average or good total fluid is, my water cut, here's my injection rate, and here's my total gas rate. My surface pressures, I've compared my casing pressure to my PSC, and I've identified that I'm on valve 2, so the second valve from the bottom. My critical rate in this case is 600 MCF. So I am actually under injecting on this well by 282 MCF. But before I go and increase my buyback, I'm going to go take a look and see what my plunger is going to need for a total gas rate, and then I can optimize the system. So in this case, if I put a bypass plunger in my well, I only need 420 MCF of total gas for this system to operate. So therefore, I don't need to buy back all of that gas. I really only need to buy back about 100 MCF of gas. So that could be a significant difference in my LOE and versus just leaving this well on gas lift. Example number 2, I've got a much lower formation gas rate. Here's my injection rate, my total gas rate. In this case, I'm on my orifice. My downhole critical rate is 355. So I'm actually over injecting by 111 MCF of gas. So I'm not very well optimized. But my bypass plunger only requires a total of 249. So I can greatly reduce the amount of injection. And in this case, depending upon how much more gas I get, I might even be able to turn my compressor off. So it'll be very close. In the third example, this is a really good well with 446 MCF of gas. I've only got 226 MCF of injection, total gas rate. I'm operating a lot higher in the well. My critical rate is 615. So I'm actually really close as far as where my total gas rate is. This is a very good example of a well where even though I'm operating higher in the system, it still makes for a very good candidate. In this case, if my casing pressures are fluctuating a lot, I could be bouncing up and down between valves 3 and 4. So if I run a bypass plunger into this well, I can very likely reduce the amount of injection that I need and actually move down a station and gain at least 500 feet of lift. And we know that if we can get deeper in our gas lift system and lift deeper, 99% of the time, we will make more production. So running a GAPL system is not necessarily just for the wells that are operating deeper in the system. It can help us greatly optimize the overall efficiency of our gas lift, as well as improve our lifting points. My last example, 244 MCF, making pretty good fluid, total gas rate of 487. My downhole critical rate is 420, so I'm very close. But again, I only need to have 294 MCF of gas in order to be able to make my system operate. So I'll be able to go and actually reduce my injection rate and again, really optimize this system and lower my total gas rate requirement by about 100 MCF. So lots of benefits for taking a look at it. And it's really good to create yourself a spreadsheet to be able to put all the information in front of you when we're trying to do these evaluations and really make things stand out exactly where it is that we can get the upside from doing this type of system. So now we'll take a look at the installation. The first thing we'll do is we'll first of all determine our operating point of our gas lift system, take a look at our casing pressure, and again refer it to our PSC column and determine where our valve is, which valve we're lifting from. We're going to make sure that we are not over-injecting or under-injecting, taking a look at our casing pressures to see whether our casing pressures are fluctuating too badly. Then we're going to determine where my plunger equipment can be installed. For the bumper spring, we'll always land the bumper spring at least one joint above our operating point, above our operating valve or our orifice. If it appears that the well is in the process of transitioning down to a lower valve because our casing pressures are fluctuating, we always want to make sure that we set the spring above the upper valve. The reason being is if we set it to the lower valve and that upper valve opens, we essentially have a hole in our tubing and our plunger may never come back up to surface. So it's much better to err on the side of having a little bit higher. And then once the well stabilizes, we drop to that lower valve, we can always go in and lower the spring down above that next operating point later on. Our guidelines for installation for the wireline guys is the same as a regular plunger system. It's really important that we still go and gauge and broach, if necessary, the tubing prior to running it to make sure we don't have any tight spots. If we're going to do this, we want to make sure that they are using their extended length gauge rings, not the small regular gauge rings. That's really critical. The little gauge ring can work its way through just about any imperfection. If they do not have an extended length gauge ring, we need to give them the plunger and let them go in with the plunger. If the plunger hangs up, we know they've got tight spots and they need to go and broach. The biggest difference is we do not need to run what we refer to as cleanup cycles. This is where we take the plunger and we run it with no afterflow, and the purpose is running it like a little swab rig, unloading all the excess fluid from the system. But because this well is a gas lift well, it's not going to be having liquid loading signs. We don't have any excess fluid, so we can just go and start immediately with our bypass plunger operations. Now we can take a look at optimization. Things are done very similar to our continuous or regular bypass plunger operation, except for we start with injection rates, where we would normally be going and taking a look at the plunger speeds and slowing our plunger down to a good arrival time by increasing afterflow. Our goal here is reduced injection. So I'm going to reduce the injection and continue to monitor my plunger arrivals as well as plunger speeds. As long as my plunger is running fast, I'm going to reduce my injection by 50 MCF and continue to monitor, keeping in mind my target gas rate. That's 70% of whatever our critical rate is. As I'm getting closer to my target total gas rate, and my plunger is still running fast, then I can go ahead and start increasing my afterflow. Because if I continue to reduce my injection, I may not have enough gas anymore to cycle my plunger. So always watching where that total gas rate needs to be, and then start increasing our afterflow to slow my plunger down and get it optimized. And again, with our bottom hole spring assembly, we're going to set it as deep as we possibly can, ideally one joint above our operating point. But we also have to keep in mind our fluid rates. If we are operating or the well still is really close to the upper limits for that particular tubing size, we likely cannot run that plunger as deep as we'd like to, because if we put it in too much fluid, we can still drown it out just like a regular plunger system. we've got really high fluid and we're operating higher in the system, we need to run the plunger higher. Essentially just take the tops of the fluid column off, reduce that hydrostatic load, and keep the plunger cycling a lot higher frequency. And then once my fluid rate starts to deplete, I can always go and start lowering my point of operation of my plunger later on in the life of the well. And then while afterflow is not as important, the more cycles we can make in the day, the better the system is going to be running. And the more cycles that we can do, this also keeps our fluid moving much more efficiently, which helps with the formation of that paraffin. So it's really important. More cycles in the day is always the best thing for any plunger system. And here's what it's all about when it comes to paraffin control. So you can see with these bypass plungers, they've done a really good job of cleaning the tubing walls and making sure that we're not allowing anything to build up inside that upper section, which can create choke points and cause us to lose production. So we'll look at some case studies. The first thing that we're going to do is that identify all the criteria. Majority of these installations were all 2 7/8. Some of them were 2 3/8. In most cases, all of these springs were set at 45 to 55 degrees, as most of them were packerless. As I already explained, we do have to take in consideration limitations of the type of plunger system that we're going to be running, but we're going to set that spring just above that operating valve or screened orifice or as deep as we possibly can. We were able to utilize our patented control system, which can tie directly into your existing automation. So we were able to take a look and monitor and optimize these wells remotely. And then we did run both styles of plungers. This is both the 2-piece as well as the dart style plunger or cage style plunger. We were able to pre-screen all of these candidates. So we would have created a spreadsheet just like I showed you and went through and identified all of the candidates that had the most upside potential to make sure that we got a lot of return on the investment. We did have all of our technicians working on the wells to make sure that they were fully optimized. We always like to make sure that we give everything the best chance, and then we provide a lot of training for our customers to make sure that the guys can go in the field after the fact for themselves and be successful. So here's our first case. So you can see that we installed the plunger on the gas well. We got lots of upside and formation gas. Here's our reduced injection, and you can see how our casing pressure came down nicely. The one thing about this example, you can see where we actually went too far, and then we had to increase our injection rate. So we went past that minimum total gas requirement, and our plunger started to fail. So we had to slightly increase our injection again to keep this well going. Our next system, you can see that we got very good positive gas. And this is a really good example where we got so much positive gas that we are actually able to turn off our compressor and release it. In this case, we were able to stabilize our fluid rates. The one thing that we have seen is that the increase in production rate on the gas side, you'll always see an increase in formation gas. Once we've improved the flow of our production inside that tubing, and get it to be more of a stabilized flow, we always see an increase in formation gas. The increase in our total fluid, we have found a direct correlation to our casing pressures. The higher the casing pressure when we first install the plunger system, and the lower we can get it, the more impact we have on upside of fluid rates. Whereas if the casing pressure is already lower and we can't make much change in our drawdown, we don't see much change in our fluid rates. And we see that in all of the shale plays. This is a good example of a well that we got really good flush production and it's stabilized after the fact. We still got good upside as well as on the fluid rates. Here's another one where we got really good flush production. And we stabilized everything. We got a slight increase in overall production, but the production was a lot more stable than what it was prior, which is another big advantage of running this type of system.